then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students. Welcome to lesson 15. Today is a very important day. It is a momentous occasion. As you can probably see by the sun beating on the side of my face, that I have a window right here. And the hope is today that you're next to a window, because when we complete this lesson and you look out that window, the world is not going to look the same anymore. In fact, you'll hear things you've never heard before. You're going to see life from a whole new perspective after today. Now, I know some of you have already done this lesson with me in pre-calculus last year, and you guys are privileged and in fact quite spoiled. But still, you want to pay attention and listen to the presentation again, because every time it gets better. So let's go ahead and get into lesson 15. So for those of you that were with me last year, I'm pretty sure you had an idea that today's lesson is over the derivative. Now notice we said the derivative, not derivative, the derivative. It is a very significant concept that we're going to dedicate a lot of days and weeks to. So let's look at today's agenda. So we're first going to go over something called the tangent line problem. It's a very famous problem. It's the problem that gives us the derivative. And then we'll look at exactly what the derivative is. And then we'll do some examples of finding the derivative. And that'll be our day. So let's go ahead and begin with the tangent line problem. So the tangent line problem is a problem concerned with finding a tangent line. So I have here the graph of a function f of x in red. So this is the graph of f of x in red. And I have 2 points on this particular curve. And I drew a line through these 2 points. And this line is called a secant line. This line is called a secant line. And of course, the line has the slope. And the slope of that secant line is called a rate of change. In fact, it's kind of called what we call an average rate of change, something you should remember from pre-calculus. And rates of change, for instance, if I was finding if this slope represented a distance over time, that rate of change would be speed. Or if this slope represented a charge over time, that rate of change would be current. Or a temperature over distance, that rate of change would be something called a temperature gradient, which is very important for predicting weather. So rate of changes are something that are very important in real life science and technology. So what distinguishes the derivative from an average rate of change, an average rate of change, of course, finds a rate of change over some particular interval of whatever your measurement is. In this case, that interval is over whatever the x coordinate represents on this particular graph. The derivative finds an instantaneous rate of change, meaning the derivative finds the slope not between 2 points, but at a single point, at an instant, not over an interval, but at a particular instant. So how can we do this, you may ask? Well, let's take a look further at this graph. And I just want to give some things some names as we look at this graph. So these 2 points, now again in red, this is the graph of f of x. So just let me make a note. This is f of x here in red. And I just want to give these points here some names so I can reference them. And so I'm going to be very generic, in fact. So this first point, I'm going to call its x coordinate x. And I'm going to call this y coordinate f of x. And that should make sense to you. So I'm using function notation, of course. So this is the graph of f of x. So if the x coordinate is x, then the y coordinate must, of course, be f of x. Now, this second point here, since the second point is going to be changing, I'm actually going to make my tangent line. So understanding a secant line goes through a curve at 2 points. A tangent line goes to a curve at one particular point. So I want my tangent line to go through X. So the value of this point is going to change in essence, which I'll show you in a little bit. So what I would like to do is denote a horizontal distance from this X value to that X value. And I would like to call that horizontal distance H. Horizontal distance H seems to make sense. And so if this X value was X and I go a distance of H, what do you think this X value should be? Sure, X plus H. And if when the X coordinate was X, the Y coordinate was F of X, then when the X coordinate is X plus H, of course the Y coordinate should be F of X plus H. Okay, so far I just named the points basically. I haven't done anything crazy or extravagant. Now again, this problem is based off the slope. And I want to begin with finding the slope of a secant line, something we're taught in our elementary algebra classes. So that's not a big deal. We know how to find the slope when given 2 points. In fact, they gave you some formula in algebra. It was y2 minus y1 over x2 minus x1. So I'm going to use that same formula. So the slope of the secant line, and my y2 is f of x plus h. F of x plus h minus my y1 is f of x. Over my x2 is x plus h, and my x1 is x. So this guy right here will give me the slope of the secant line. I can simplify my denominator a little bit, where I get f of x plus h minus f of x over h. Okay, so that will give me the slope of the secant line, and that's cool. This is something that's called a difference quotient. So I'm gonna make a note of that. This is called a difference quotient. Of course, everything in math, the words make sense. We're taking a difference and we're taking a quotient. So that makes sense. Now again, that's going to give me the slope of the secant line, which is stuff we know how to do. There's nothing revolutionary about finding the slope of the secant line. The title of this problem is the slope of the tangent line. And I want to get a tangent line right here at this point, X. So how is that going to work? Well, if I want to get a tangent line right here at this point, X, then that means this point, X plus H, needs to get closer to X. I need to make this point X plus H get closer and closer to X until it's right on top of X. That's what I need to do. But how can I do it? So let's look back again at our difference quotient. So again, for this to change from the slope of the secant line to the slope of the tangent line, I need this point, as I just illustrated, to get closer and closer to this point, to really it's right on top of this point. Now, think about this. As this point gets closer to this point, what happens to the value of h? Again, as this point gets closer and closer to this point, what can we say about h? Is h going to get bigger or smaller? Hopefully you're saying h is going to get smaller. So the closer and closer x plus h gets to x, h gets smaller. And guess what's the value of h when this point is right on x? 0. Think about it. If h is 0, x plus h equals x. So therefore, to find the slope of the tangent line, we can simply take the limit of this difference quotient as h goes to 0. So the slope of the tangent line, I simply can take the limit as h goes to 0 of the difference quotient. So that's f of x plus h minus f of x over h. And ladies and gentlemen, that was pretty quick, because guess what? The slope of the tangent line is what we call the derivative. So the derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. There it is. You now know the formula. Now, this may be an innocent looking formula to you, but this formula is so powerful and encompasses so many things. It is of tremendous importance and is one of the most significant discoveries in human history. But for right now, this does many things that we'll learn throughout the course of the class. But for right now, all it does is tell you the slope of a tangent line. So please keep that in mind. For right now, this formula is just going to tell me the slope of the tangent line of some function f of x. That's all it's going to tell me for right now. Later, it's going to tell me a whole lot of different things. But for right now, it's just going to tell me the slope of a tangent line. So when you think about derivative, think about slope, and think about slope of a tangent line. So let's just find the derivative for a few functions. Let's say f of x equals x squared. So that's my function. In fact, let's say x squared plus 3. So that's my function. I'm going to find the derivative. So we got several notations that represent the derivative, and as they become needed, we'll look at them. So I want to introduce one right now that I use. So this notation, f prime of x, that means the derivative of f of x. So when I find this derivative, I'm going to refer to it, I'm going to use the notation f prime x for this particular derivative. Okay, so let's look at it. So let me remind myself of the formula. So f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. That's my formula. So if you look at the formula, we know what f of x is. It's given. H is just h. So really the only thing we need to actually find in the formula is f of x plus h. So we're just going to find f of x plus h, and then we're going to subtract f of x from it and see if we can find the limit. So first, let's figure out what f of x plus h is. So f of x plus h is x plus h squared plus 3. So that is x squared plus 2xh plus h squared plus 3. So there is f of x plus h. So that's f of x plus h. And again, what we're going to do is we're going to do f of x plus h minus f of x. So let's write that. So I'm doing the formula. So I'm doing this formula right here. So f prime of x is the limit as h goes to 0 of f of x plus h. Here's f of x plus h. So x squared plus 2xh plus h squared plus 3 minus f of x minus x squared plus 3. And notice we put f of x in parentheses, so the minus sign gets distributed to all the terms of f of x. That's pretty important. And of course, over h. So we want to find this limit. And we're familiar enough with limits to see that there will be a problem the way it is constructed right now, because if I plug in 0 for h, I'm going to have 0 in my denominator. So I need to be able to take that 0 out of my denominator before I can plug this 0 in. So let's see what happens when we subtract up here. So some things are going to cancel quite nicely. X squared, 3, 3. So what we're left with on the top, limit as h goes to 0, is 2xh plus h squared. That's it, over h. Now you may notice that both these terms have an h in them, so we can divide by h. So this is the limit as h goes to 0 of 2x plus h. So this is just me dividing both these terms by h, and I have to divide both of them by h. And now I'm able to plug in 0 for h. Since I got this h out of my denominator, I plug in 0 for h, and I get 2x. So f prime of x for this particular problem is 2x. Now again, this derivative is a function, but I talked about it representing the slope of the tangent line. Well, the slope of the tangent line depends on the value of x. So if you look at P as my tangent point, for example, as I choose different values of P, you can see the slope of the tangent line changes. So the slope of the tangent line depends on the value of the x coordinate where it is located. So for instance, if I wanted to know the slope when x was 3 per se, I will plug in 3 to this function. That slope would be 6. The slope of the tangent line when x is -4 would be -8, so forth and so on. So the value of the slope depends on the value of the x coordinate of the tangent point. So in many cases, our derivative is going to be an equation because the value of the slope of the tangent line varies. Now, there are, of course, occasions where the derivative is a constant. So the derivative can be a constant, but in most cases, it's going to be another function. But anyway, we had our original function was x squared, and its derivative was 2x. Oh, excuse me, our original function was x squared plus 3. I'm sorry. Our original function was x squared plus 3, and its derivative was 2x. I'm pointing that out because you just want to compare the derivative to the original function each time you find one. Let's do another example. So here, let's say my function f of x is x cubed minus 11. And so I want to find f prime of x. That my prime mark could have looked a little better. So I want to find f prime of x, the derivative of f of x. Okay, so of course, f prime x is the limit as h goes to 0 of f of x plus h minus f of x over h. So I need to figure out what f of x plus h is. So f of x plus h is x plus h cubed minus 11. And x plus h cubed is x cubed plus 3x squared h plus 3xh squared plus h cubed minus 11. And if you forgot how to cube a binomial like this, it's binomial expansion, and we use something called Pascal's triangle. So if you recall, it's not the most difficult thing in the world to do. So this is f of x plus h. And again, we want to do f of x plus h minus f of x. Let me do it here vertically. So let's put what f of x is. f of x is x cubed minus 11. So if I do this difference, what's going to happen is these are going to cancel and those are going to cancel. So I'm going to be left with this over h, of course, and I'm going to find that limit as h goes to 0. So let me write what I have left. So f prime of x is the limit as h goes to 0 of 3x squared h plus 3x h squared plus h cubed all over h. And again, the problem is I can't plug in 0 for h because the h down here. But if you notice, every term up here has an h in it, and that's one of the beautiful things about this whole process. Once you do your subtraction, everything that you're left with has an h in it, and you can easily take the h out. That's of course the deal when you're dealing with polynomial derivatives. So if I divide everything by h, what I'll be left with is 3x squared plus 3xh plus h squared. And if you plug in 0 for h, everything with h is going to turn to 0, and you're going to be left with 3x squared. So the derivative of this case was 3x squared. And again, the original function was x cubed minus 11. Okay, I'm going to do one more example. So let's say f of x is x to the 4th plus 10. And we're going to find the derivative, of course. Find f prime of x. Okay, so you know the formula. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. Now again, it's very important to know this formula and to be able to use this formula. So I know some people from last year are saying there's a shortcut, and there's a shortcut we can use here. And maybe there is a shortcut, which I'll cover a little bit later. But you are going to encounter derivatives that you do not have a shortcut for. So you always must be cognizant of this formula and be able to use this formula when needed. So I'm not using this formula superfluously, just trying to show off and doing all this technical stuff. This formula is indeed needed, and understanding what this formula represents is also extremely important. So let me carry on. So I need to find f of x plus h, which would be x plus h to the 4th plus 10. And so that would be, I'm gonna give myself a little bit of room. So that would be x to the 4th plus 4, x cubed h plus 6, x squared h squared plus 4x h cubed plus h to the 4th plus 10. So that's f of x plus h. And of course, f of x was x to the 4th plus 10. So when we do our subtraction, this guy would cancel along with this guy. And so what we will be left with so if we take the limit, I'm finding f prime of x, the limit as h goes to 0. So what do I have up here? I have a 4x cubed h, a 6x squared h squared, a 4x h cubed, and an h to the 4th. All of that junk over h. Everything has an h in it, so I'm going to divide everything by h. And it gives me the limit as h goes to 0 of 4x cubed plus 6x squared h plus 4x h squared plus h cubed. And again, to find this derivative, to find this limit, excuse me, I'm gonna plug in 0 for h. So everything that has an h in it is gonna turn to 0, 0, 0, 0. So I'm left with 4x cubed. So f prime x is 4x cubed. And again, the original function, just for comparison, just want to kind of juxtapose the derivative with the original function. The original function was x to the 4th plus 10. And I said this was my last, excuse me, that wasn't even showing. I said this was my last example. So if you notice thus far what I've been doing, I started off with x squared plus or minus a constant. Then I did x cubed plus or minus a constant. Now I did this x to the 4th plus or minus a constant. Before I close, I want to just do x. So let's say f of x is 5x minus 3. Now I want you to think about this for a second. Now, when I'm finding this derivative, what I'm doing in every case is I'm finding a function that gives me the slope of a tangent line. So you have a curve, you got a little point, and you draw a little line on there. And in many cases, that slope differs on the value of x. Well, this function is a line, correct? So if I pick any point on this line, don't we already know what that slope would be? So just think about that for a second. While you think about that, I'm going to go ahead and find f prime of x. Find f prime of x. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. F of x plus h is 5 times x plus h minus 3. So that's 5x plus 5h minus 3. That's f of x plus h. F of x is just 5x minus 3. And if you cancel, the 5x is going to cancel. The minus 3 is going to cancel. You'll be left with 5h. So f prime of x is the limit as h goes to 0 of 5h over h. That would cancel. And so we just get 5. Notice this derivative doesn't depend on the value of x. There's no x. It's just a constant. And guess what? It's 5. And what's the slope of this line? You know, from algebra, the slope of this line is 5. And that is because if the function is a line, if I choose any point on the line, the slope is going to be the same. Choose any point is going to have a slope of 5. That's different from, a function like this. A function like this, a tangent line here would have this slope. A tangent line here would have this slope. And basically the slope will be different on every different value for x. But when you have a line, the slope is the same on every point that touches the function. And that's why the slope of linear functions are constants. The slope of linear functions, the derivative of linear functions are constants. So before I end this, I just want to remind myself of all the answers I got for each problem. So I'll write this one down. In this case, f of x was 5x minus 3, and its derivative was 5. And then in another example, let's see, another example, f of x was x to the 4th plus 10, and its derivative was 4x cubed. And another example, let's see, f of x was x cubed minus 11, and its derivative was 3x squared. So again, I'm just summarizing the solutions that we just worked out, just for comparison's sakes. In the first one we did, that function was x squared plus 3. So in our first problem, let's see if I can write it here, f of x was x squared plus 3, and its derivative was 2x. So I want you to look at the original function and its derivative. And you know, math is all about patterns. And I want you to see if you notice any patterns. So just look at these answers, look at the function and their derivatives, and see if you notice any patterns. And we'll revisit this concept tomorrow. See you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.